Next, we are going to move to our first panel. This is our research and development panel, and our moderator is Dr. Lou Qualls. And so let me briefly introduce Lou. He is a distinguished researcher in nuclear energy and fuel cycle division at the Oak Ridge National Laboratory. He serves as the Nuclear Energy and Fuel Cycle Division Reactor Technology Integration Lead and has extensive experience in both fission and fusion energy research. So with that, I will turn it over to Lou to begin introductions of his panel.
Thank you very much. Welcome everybody to the first panel. And the topic is research and development. And the tagline is research and development technologies, opportunities, and partnerships in fusion. We'll have 4 panelists today: Dr. Kathy McCarthy, Dr. Mickey Wade, Dr. Dennis Youchison, and Dr. Livia Casali. The first panelist is Dr. Kathy McCarthy. She needs no introduction because Jim gave her a great one earlier, but I wanted to add something to it real quick. She is a member of the National Academy of Engineering and has received 2 American Nuclear Society presidential citations, both related to fusion. She served on the Fusion Energy Sciences Advisory Committee from 1999 to 2013, and on the U.S. ITER Technical Advisory Committee from 2010 to 2013. With that, Dr. McCarthy.
Thank you, Lou. That just tells you how old I really am. All right, I think that the slides will be pulled up by somebody other than me, right? It came up, it went away. The joys of Zoom. Can we try that again? There we go. All right, so I'm going to give you a very brief overview of where things are with the ITER project and how they fit into the bigger conversation that we're having here today. If you can go to the next slide, please. So first of all, generating electricity from fusion requires resolution of 3 major scientific and technical challenges. The first one's creating and sustaining a fusion power source. And you can see here, that's really where the technical readiness is the most advanced. Other areas that are required to reach that energy goal: materials to survive in the fusion environment and fuel self-sufficiency and harnessing fusion power, especially the last one, are much less mature. All 3 of these things need to come together in order to make fusion electricity a reality. Next slide, please. Now, what I'm going to talk about is specifically the creating and sustaining a fusion power source. And specifically, I'm going to focus on ITER. ITER will demonstrate and sustain this performance in fusion power dominated regime. This is called a burning plasma, which just means that it is self-heated. And you're going to hear a little bit more information on the other categories from other panelists. Next slide, please. In terms of an overview, I already talked about what the mission of ITER focuses on a self-sustaining plasma. It's really to demonstrate the scientific and technological feasibility of fusion energy. This is important. It will demonstrate on the order of 500 megawatts for pulses up to 3,000 seconds. It's an international project with the partners being the European Union, which is the host, China, India, Japan, Korea, Russia, and the US. And each of the partners, with the exception of the host, who owns a bigger share, is responsible for 9% of the construction costs. But for our 9% investment, we receive 100% of the ITER science and technology information. During operations, the US will contribute 13%. Next slide, please. Just a little factoid for you. Vladimir Putin signed the ITER agreement back when it was originally signed some time ago. This is the ITER site in southern France. What you see in the center of the picture is the tokamak building. This was actually a greenfield site to begin with, so lots of progress, and this is from May of 2029. If you can go to the next slide, please. Construction is about 78% to first plasma. In France, this is being categorized as a nuclear installation. ITER is a nuclear installation and is regulated by the French regulator. It will, at first plasma, demonstrate the largest vacuum vessel in the world, largest cryo plant, and will have over 10,000 tons of superconducting magnets with a combined stored energy of 51 gigajoules. Next slide, please. Assembly of the actual tokamak started last summer. If you want to get more information on this, if you go into YouTube and Google ITER Start Assembly Celebrations, you'll actually see some really interesting information on that. The Director General walking you through the facilities. But what you see right here is what was considered one of the most challenging lifts in the project. This is the cryostat base. It weighs just over 1,200 metric tons. It's the heaviest single lift of assembly, and it had to be placed within 5 millimeters. So this was an engineering feat, and they did it successfully. And one of the things I want to point out that you learn from things like this is a lot of times it's not the rocket science that gets you, right? It's the engineering. And of course, being an engineer, I think that what we do is very, very important, but the assembly teaches you a lot. Next slide, please. I'm going to go through a series of photos just to give you an idea of where things are in terms of construction. This shows you the vacuum vessel sectors. They're in preparation for assembly. There are 9 of the sectors. They're being provided by the European Union and Korea. Next slide, please. And it looks like maybe it's, there we go. Not sure about the resolution. I'm just going to keep going. Hopefully others, the resolution isn't messed up. For some reason on the last couple of slides, it's gone all fuzzy. But what you see here, there we go. Now it's getting clearer. The first magnet has been installed in the base of the tokamak pit. This is the colloidal field coil number 6. So again, progress on the tokamak itself, and this is quite exciting. Next slide, please. What I'm going to talk about now is what is the U.S. responsible for, and how what we do ties into the broader fusion community. So U.S. is responsible for just over 9% of the construction costs, and it's actually, I think, 9.09% if you want to get technical. These are the different systems that we're responsible for, and I'll point out for some of the systems, for example, diagnostics, there are multiple diagnostics that we are responsible for. So rather than just one, it is multiple. And some of these things are actually complete already. The US provided 75% of the steady state electrical network. That was the foundation on which the ITER facility was then built. That's done. And we also provided 8% of the toroidal field coil conductor, and that also is complete. And then for the other systems shown here, they're in different stages. Some are actually under procurement, some are in design. So depends on the specifics on the particular hardware component. One of the really important things that we're gaining from this in the US is the ability to write specs that can then go to industry so that they can fabricate the components that need to meet regulatory requirements. Of course, in the US, the Nuclear Regulatory Commission is looking at regulating how should advanced nuclear, including fusion, be regulated, looking at they're developing a new framework for that. But overall, there's going to be a need to meet specifications. So industry doesn't need to know how to do that, how to write the specs. That's the job of all of us, but they need to know how to meet them. And that's one of the things that we're gaining from the ITER project is that evidence, that ability for US industry to meet these specifications, and of course, for all of us to write them. Next slide, please. I mentioned that there are already some things that have been delivered. The steady state electrical system, you see that in the upper left-hand corner of the slide. Here in the center is the niobium tin strand. US provided 8%. Over to the right are magnet supports. Again, another piece of hardware that's being delivered. These magnets have to withstand very, very large forces, and so they need to have these sorts of supports. Down here, in the middle, you actually see a surge tank. It's these sorts of things that people don't always think about when you think about how do you build one of these power plants. It's a whole variety of components that have to come together. Next slide, please. The US is responsible for the central solenoid. It's considered the heart of ITER. You can see here in the center, it's 6 modules stacked. There's also a spare. It is quite large, has large energy capacity, and this is the largest superconducting magnet, most powerful superconducting magnet under construction to date. And if you go into the next slide, what you will see is the first of the 6 modules is en route to France, and see in the upper right-hand corner, that's actually the module. It's of course all shrink wrapped and protected. This is at General Atomics. They are fabricating the module. And then if you go to the next slide, what you'll see is the module convoy actually going across the country. This is in Eloy, Arizona, a place probably very few people know of, and it's not a place you would go, but it's a place you go through. But as it's moving from Poway in Southern California to the port of Houston, this was the path that it took. My sister and her family actually went out and took pictures and sent them to me. And it will arrive in France in end of July, early August. Takes a boat, obviously, from Houston to France. Next slide, please. And Tennessee Industry is delivering essential components and providing essential project support. These are just some of the examples. Electron cyclotron heating transition lines. This is a plasma heating device, and 4 kilometers of line are being fabricated to transfer 20 megawatts to the plasma. And you see down in the lower right, transmission line expansion unit prototypes are being produced by ARMEC here in the city of Oak Ridge. And then if you go to the next slide, this one is put in not so much for you to read it, although I think probably slides will be made available, but just to give you an idea of just Tennessee Industry that is providing components, providing support to US ITER. So there's over $153 million that has been provided to Tennessee Industry to develop and fabricate components. Next slide, please. Then overall, from a US perspective, there's been over $1.2 billion awarded to US industry, universities, and national laboratories to enable the design, fabrication, and delivery of components. You can see we've got all but 3 states covered. We still keep working on those 3 states. So if you know anybody from North Dakota, Louisiana, oh, and I always do this, Alabama or Mississippi. I think it's Mississippi. See, this is a Westerner talking to you. Apologies for that. But we'd love to get them engaged as well. But again, this is really important in terms of training industry to really to position industry for that future fusion economy. Next slide, please. We just have a couple more things to wrap up before hand it over to the next panel member. So what does ITER mean for US fusion? There have been a multitude of reports that have come out. Most recently, the National Academy is bringing fusion to the US grid. And these reports all are clear on the fact that ITER occupies a very important role in the fusion program. The capabilities, expertise that are being developed, have been developed, and continue to be developed through ITER are really enabling the US fusion industry to be where they are today, and the potential step to a fusion power plant, fusion pilot plant. Next slide, please. This is a list of activities under ITER that benefit what's going on today, will continue to benefit the development of even these alternative confinement devices, because there's a lot of shared technologies in all of this. So one of the things that's really important is getting the word out. And one thing I would say too is you learn a lot from scaling up. ITER was designed based on known technologies, things that have been demonstrated, at least at a smaller scale. You always learn things when you scale up, and the integrated operation of these things teaches you as well. So important for everything that we're doing across the fusion community. Next slide, please. I'm going to lead things with the recommendation that came out of the 2021 National Academy's report on a fusion pilot plant. And it was really encouraging the United States to move forward with designing a fusion pilot plant, enabled by all the work that's going on in the fusion community, and really through that design process, understanding where the gaps are. And with that, I will now turn it back, I think, to Lou, and we can move on to the next panelist. So thank you very much.
Okay, thank you. That was an excellent presentation. I wanted to remind folks that at the end of the panelist, we'll have time for questions. So if you wanted to type in your question in the chat box, we can ask Kathy questions later about her presentation. Our next speaker is Dr. Mickey Wade. He is the director of the Fusion Energy Division at ORNL. Prior to that, he was the deputy director of the Magnetic Fusion Energy Division for General Atomics, where he served as the D3D National Fusion Program Director and D3D Experimental Science Division Director. He was named a Fellow of the American Physical Society in 2010 for his outstanding contributions to burning plasma physics, impurity transport, and the development of advanced tokamak scenarios. He received a bachelor's degree in nuclear science and engineering from Virginia Tech and a master's and doctoral degree in nuclear engineering from Georgia Tech. With that, Dr. Mickey Wade.
Thanks, Lou. I appreciate it. As Lou said, I spent about 15 years as working with General Atomics, and have spent 15 years before that at the lab. I just recently returned right at the beginning of the pandemic to this job at ORNL. So I have a pretty good perspective both on the private side of opportunity space and also on the government supported side. So hopefully I'll lead you through that some in this presentation. So next slide, please. I think one of the things that Jay mentioned earlier today, well, actually, there's just an outline here. I'm going to go through long-term prospects, give you some idea what the long-term is, intermediate objectives, and what I think there are some opportunities in East Tennessee to capture economic growth and opportunity, and then some near-term opportunities that I think are immediately available today. So next slide. So Jay said this earlier. I wanted to capture it in graphical form because I think this is like the best graphic I've ever seen of what the coming energy demand is going to look like worldwide. This is a plot. It actually comes out of the Intergovernmental Panel on Climate Change Model Database. I just grabbed the data from it and organized it in a particular way. And it's the required electricity capacity versus year. And you can see that there's an enormous growth. This is mostly due to Southeast Asia, African growth, but also due to electrification of the transportation sector. But because this particular model imposes a 2-degree temperature rise, the amount of power you can produce from CO2 producing gets clamped in about the 2050 timeframe. So this means this large increase that occurs subsequent to that has to be done by non-CO2 producing sources. If you look at this is 25,000 gigawatts. That's 25,000 gigawatt electric plants. If you looked at 2018 at our solar and wind power, we have a total of 163 gigawatts, and we were adding about 20 gigawatts each per year. So we're not going to get there using that mode of operation. So we need other power sources. Next slide, please. More importantly, probably for this particular audience, is that I think this same model produces what they think the cumulative capital investment would be in energy. So this isn't fusion specifically, but in energy. And you can see just an enormous rise in this in the latter half of the century. And just if you look at the right-hand corner of that, you'll see by 2100, the market is expected in 2005 dollars to be $2.5 trillion. Just for reference, the 2018 market for cell phones was $0.5 trillion. So this is an enormous economic opportunity for both states competing against other states, but also countries competing against other countries in terms of economic wealth going into the next century. So next slide. So I think fusion, as I'll show, fusion has a lot of benefits. I think you're aware of a lot of these. I just want to give you a flavor of what fusion provides for you. If you try to provide a gigawatt electricity for a day, this is about 1 million homes. You need 8 million kilograms of coal, or 80 railroad cars of it. Produces enormous amount of waste. Fusion, you only need 3 of these little bottles of deuterium and tritium, and it produces just a modest amount of helium as its waste. So from that point of view, it's very efficient and not waste producing. A bigger aspect, I mean, if you sort of compare this to the land use needed for a renewable, to do the same amount of energy by solar panels, you need 3 million of them. And if you did it by wind turbines, you need about 400. If you've ever seen these wind turbine fields, 400 wind turbines would take up a huge amount of land space also. So anyhow, so fusion has a lot of benefits, and I think it's not, in my view, it's not a matter of if we have fusion in the future. I think it's a matter of when. And the question now is how aggressive we should be and can be with regard to developing fusion on the near term. So next slide. So I'm going to talk a little bit now about intermediate objectives. So next, the next slide. Kathy alluded to this in her talk. The National Academy just had a report come out in the December-January timeframe, and it basically calls for a very progressive timeline for a fusion pilot plant. And they're looking at meeting that curve that I showed earlier in terms of energy demand in the last half of the century, green energy or non-CO2 producing energy. And they come up with a timeline that you need to have a fusion pilot plant operating in the 2035 timeframe. Now, this is technically challenging, it's fiscally challenging, but in their view, they did not see a reason why it couldn't be accomplished, given the appropriate resources and the appropriate breakthroughs and innovations needed to make it happen. So I think this is a statement by someone outside the fusion community. National Academies is separate from the fusion community. That's making a statement that this is a time that we can really make an aggressive push in fusion. So in terms of ORNL and what that means for East Tennessee, next slide, please. We are very interested in being a part of this future. We have the capabilities and the interest to host a fusion pilot plant and any demonstration facilities that are needed to put a fusion pilot plant on a better footing. We have the vision of that fusion is a clean energy electricity source for this generation and beyond, not waiting beyond this generation. And we have multiple siting options. I show the Oak Ridge Reservation there, sort of high-level view. There's lots of land. We have done studies to look at various areas where we could site such a facility. We have a demonstrated capability to host major projects. We have SNS, we have HIFER, we have the exascale computing project. So we have the ability to do that. And we have a broad range of capabilities within our staff that are important as pilot plant success, both in terms of energy production on the fusion side, but also electricity generation once you produce the thermal energy. So our vision for this is that this would be a public-private venture that leverages the capabilities of both sectors to deliver timely completion at acceptable risk. I mean, there's also schedule risk as much as there is technical risk in this, and that's where the private firms provide some leverage in moving these things forward more aggressively. One thing I do want to say for 2040's delivery, or even 2035 delivery, if you want to go back that early, a conceptualization and build out of the infrastructure will need to begin in the 2020s. You saw this enormous site that ITER is on. If we have to start from a green field when we start the pilot plant project, then that will be an enormous time delay potentially, but also an enormous amount of cost that we'd have to do. So if we can envision and carry out projects before that, that would be constructive to that infrastructure build out that's needed for a fusion pilot plant, that would put us much further along in realizing fusion energy. So next slide, you can just flip to the next one. Next one just is just the outline again. Near-term opportunities, go to the next, so the next slide. So I think there's several near-term opportunities for impact. Kathy showed this slide earlier, but this is essentially, if you look at these recent reports that have been come out, there was a burning plasma report from the National Academies in 2018 that was followed by a community plan that was developed in 2020, and then a FISAC plan that was issued in the report to FISAC was done in late 2020. The actual report was finalized in 2021. It basically outlines these three areas of development. So what I want to key in on here is that we're pretty, and this, if you look at this color scale, this is sort of trying to capture where we are in technical readiness. So this is, if you're trying to build this fusion facility of the future where you have technical gaps you need to fill. Most of the research and development that has occurred to date in the US program, or worldwide even, has been on this top line in creating and sustaining a fusion power source, and ITER will take that even further. I'll also comment that many of the private firms that are developing ideas to accelerate the timeline for fusion, most of their efforts is in this line in terms of how to make a better fusion power source. Now, but there's two very important aspects that you really have to take into account in fusion. One is materials that survive in the fusion environment. This is a extreme environment in terms of heat flow, heat fluxes to the materials, but also the neutrons that are produced by the fusion process itself. And then you have to have fuel self-sufficiency and capture that fusion. I don't know that it's well known, but tritium is not readily available in the world. And so you had, that was a question on this earlier. You have to produce that on the fly, typically to, in most scenarios that people have looked at if you're using the DT cycle. Even though there are a lot of ideas out there, there's not been very much research or development on either producing the tritium or extracting it from whatever materials that produce it. And so this is, in terms of technical readiness, it has a long ways to go. So next slide, please. So in terms of what are the opportunities going forward with regard to near-term opportunities, I think there's a lot of technical opportunities. These could be potentially supported by DOE cost share programs. One of those cost share programs is the INFUSE program. I think Dennis will talk more about that in the next talk. But they're also envisioned by FES and DOE to have even larger cost share programs. Those have actually been written into bills by Congress, and on the authorization side, they have larger cost share programs. Those have not been funded yet, but they have been authorized. And particularly, I think there are some areas that are of importance from developing these lower two lines of technical opportunities. One is new materials that meet the rigors of fusion. Like I said, this is not an easy challenge for materials. Advanced manufacturing of highly complex components. These are components that have to deal with a myriad of extreme constraints, but they have to work efficiently and robustly over long periods of time. And so advanced manufacturing, I think, will be a key aspect of making that possible in the future. We need vacuum and gas separation systems that can take this tritium and separate it efficiently and get it back into the system in a timely manner. The larger the tritium inventory you have on site, the more expensive the facility will be, the more regulated it will be from the point of view of tritium security and safety. And then finally, advanced simulation design of fusion systems. As I've said, these are complex systems. They live at the edge of virtually every area of the performance of each component lives at its margin. And so we're going to have systems designs that take into account the integration of all those components into a single system. And so simulation design will be a critical aspect of that. And now finally, there's facility construction. There are existing projects. Kathy went over what opportunities there are with the ITER project, but Oak Ridge is now in the process of starting construction of the MPEX, which is a material testing program. This is the first time that we'll encounter things such as long steady state operation of magnets, high heat fluxes, 10 megawatts per meter squared for days on end that we'll have to handle. So this is, we're going to be encountering new things that are important for fusion in the future in these, and therefore technologies that can handle that will be of utmost importance. And then finally, I think there is a potential for public-private demonstration facilities. We have embarked internally on, streamlining this with regard to how private enterprise would engage with the lab. on siting potential facilities. We have not finalized that, but we're in the process of doing that. But once those are there, there'll be a lot of opportunities for local industry in terms of site preparation, construction firms, also utility services, electricity, water, et cetera. But also support systems that, technology systems that are needed to deliver RF power or materials that can function for long periods of time. So I think there's a wealth of opportunities in East Tennessee, and I think Oak Ridge wants to be a resource to the community, not just of East Tennessee, but the fusion community at large, in being able to aggressively deliver on fusion energy in the next few decades. Okay, thank you. That's all I have.
Okay. Thank you, Mickey. That was an excellent overview. I appreciate it very much. Our next speaker is Dr. Dennis Youchison. Takes me a minute every time to get that. Is the director of the Innovation Network for Fusion Energy, or INFUSE, a public-private partnership program sponsored by the DOE, Office of Science, Fusion Energy Sciences, and managed by ORNL and PPPL. His research interests include high heat flux testing of plasma-facing components, computational fluid dynamics, helium cooling, plasma material interactions, and blanket technology. His research is focused on the development of materials for extreme environments and the design of plasma-facing components in advanced high-temperature heat exchangers for fusion reactors. He received the BS and MS and PhD degrees in nuclear engineering from the great Pennsylvania State University. He is a licensed professional engineer in the state of New Mexico. He holds 5 patents and is a senior member of IEEE. With that, Dennis.
Very good. Thank you, Lou. Appreciate the introduction. I do have one slide here, so we'll keep it simple. I'm limited to about 10 minutes. What you see on the left of that slide is our website for INFUSE, which is, Lou said, is the Innovation Network for Fusion Energy. That's essentially our public storefront. You're all welcome to go browse that site. There's a URL there in the middle. There's actually quite a bit of information there regarding the program, requirements, et cetera. I just want to kind of go through it, but basically for the benefit of the private companies here in Tennessee that might be interested in participating in the program and throughout the nation. It started as a pilot program in 2019. It was loosely modeled after GAIN, which was a similar public-private partnership for fission energy. Although this is administered through the Office of Science, and so we follow the Office of Science policies as far as reviews, et cetera. As Lou said, I am the director. I have a deputy director at the Princeton Plasma Physics Laboratory. That's Dr. Ahmed Diallo. And as he said, the program is actually there to help private companies overcome the technical hurdles to energy commercialization and to accelerate the development of fusion energy. So I briefly just wanted to say, explain how it works. So it starts by companies initiating an RFA, which is a request for assistance. And any company registered in the United States can do this. And it's the RFAs can be submitted during 2 submission cycles, which are 6 weeks long. The next cycle actually starts tomorrow. And the RFAs undergo a rigorous scientific peer review with 3 subject matter experts. And the reviewers score these, and that helps FES select the most promising projects for an award. The INFUSE projects have an 80% government share and a 20% company co-share. The government funding goes directly to the national lab, and there's no direct funding to the companies themselves. So INFUSE also assists in placing CRADA contracts between the labs and the companies. We also help to share the technical information, and we actually on that website, we maintain a library of government reports and materials data, et cetera. And another purpose we have is to help access or provide access to government facilities, that's experimental facilities, as well as high performance computing resources throughout the DOE complex. I should point out that INFUSE has 10 member laboratories, DOE national labs, and most of them are engaged in fusion research, active fusion research for the Fusion Energy Sciences program. At those 10 research institutions, there's a point of contact at each one who's responsible for running the program at that lab. We also host an annual workshop to showcase the progress and share information. We sometimes co-locate with the Fusion Industry Association, with RPE, and last year we did it with EPRI. So what about the future? Well, we're trying to expand. One of our mandates is to try to involve universities as well as the national labs. It's a little bit challenging because universities have a completely different funding mechanism. And so the Fusion Energy Sciences is looking into the legal ramifications of how we best set that up. But it's certainly in our mandate to broaden the program to also fund universities doing research in fusion. We also hope to expand into these larger sort of $1 million plus specific technology demonstration programs that'll be hosted at the labs. And those are specific programs into various technology aspects such as blankets, high temperature superconducting magnets, pellet fueling, et cetera. And then, although we won't likely, INFUSE itself won't likely be part of this milestone program or this cost program that's coming out, that likely will be managed by the Fusion Energy Sciences directly. We will probably assist in handling some of the management functions. So what are the issues that are faced by INFUSE? Well, you know, it's a government program, and as such, we don't pick winners and losers. We respond to the direct interest of companies, although we do value the overlap with a broader program. And we entertain both magnetic fusion and inertial fusion, and also hybrid concepts, and they're given equal consideration. We are also instrumental with working with university students, interns, and postdocs, and we try to help with the workforce development that this growing industry is starting to face. Many of the private companies involved are actually looking to hire professionals in this new field of fusion engineering. The public-private partnerships are built on the base of our government program, and that actually supports the private-public interactions. And so we need to support both the base and expand it to include the private partnerships. If you look at the right side of the slide I show there are 40 awards since the inception of INFUSE, and representing about $9.93 million, 40 projects. The latest cycle had 9 awards for a total of $2.9 million. We also welcome General Fusion's office siting, that is good news in the East Tennessee area. We're optimistic that other companies will follow, and that'll further enhance the collaborations with Oak Ridge National Lab and the INFUSE program in general. And we look forward to the milestone program and larger INFUSE demo projects. I believe that's all I have. I'll turn it over to Lou.
Okay. Thank you very much for that, Dennis. I appreciate it. If you have questions for Dennis, be sure to put them into the chat, and we'll get to them after our final panelist. Our next panelist is Livia Casali. She is the Edge Core Integration Area Leader for the DIII-D tokamak at General Atomics, and is an incoming assistant professor and Zinkle Fellow at the Nuclear Engineering Department of the University of Tennessee-Knoxville, beginning in August 2021. As the leader of the Edge Core, the Core Edge Integration Area for DIII-D tokamak, her work is focused on the role of radiative diverter and impurity behavior to achieve high performance operating scenarios. She works on both experiments and computational modeling, and she led the first impurity seeding experiments in the newly installed slot diverter at DIII-D. She received her PhD from the Max Planck Institute for Plasma Physics in Garching and the Ludwig Maximilian University of Munich, for which she was awarded the EPS and PPCF prize at the European Physics Society Conference. And from the Italian Physics Society, she received the award for highly proficient scientific activity, named in honor of Pietro Lacerna, the founder of the Italian Physics Society. With that, Dr. Casali.
Thank you so much for the introduction. So my name is Livia Casali, and I'm the Core Edge Integration Area Leader for the DIII-D tokamak. The D3D tokamak is the largest tokamak in the US and is located in San Diego. I'm showing the tokamak here in this picture, and I'm also showing two pictures of myself working inside actually the vacuum vessel of the tokamak on some diagnostics. D3D is a very collaborative environment, as the all fusion award really is. There are over 700 user scientists from more than 90 different institutions, and is hosted and operated by General Atomics, where I am a staff scientist. I'm currently in the process of relocating to Knoxville, in fact, in the next a few weeks to start my appointment as a new faculty at the Department of Nuclear Engineering at the UTK. I am very honored and very excited for this opportunity to join such a great department, which also has a division of expanding the fusion program towards the core edge integration area, which is my area of expertise, and where which is going to be really key for ITER and for the design of a future power plant. So I'm going to try to talk in the next few minutes a little bit about these challenges that we are facing in fusion. I'm showing here on the right, this is a full-scale model of the cross-section of D3D. I'm actually standing on a kind of a tall ladder here just to give you the idea of the dimension. And my research is focused on integrating the hot core of the plasma with the cold edge. So the issue is that we need to have the core extremely hot, 10 times hotter than the sun. That's right, because we need to make fusion right here in the center. However, at the edge, we need to have low temperatures because we do not want to melt the wall. So this just gives you the idea of kind of the challenge that we have ahead. So in order to do so, we need to dissipate the heat and particle fluxes, which comes from the core and they flow towards the edge before they reach the wall. So this is called the core edge integration challenge. If you can go to the next slide, please. So now, because the core and the edge of the plasma are guided by very different physics, bringing the two together in high fusion performance, reactor relevant scenarios really represent a great challenge in burning plasma science. This has been identified by the National Academy of Science as well as by many of the community reports. So, one thing is that I have dedicated a lot of my research in diverter and core edge integration by, for instance, injecting impurities in what we call the diverter. Diverter is, I'm showing here in the central part of this figure in square, is this device that removes the heat and particles from the plasma. And in the center, I'm showing just an example of the ITER diverter. So this is how the ITER diverter from a simulation is looking like. So now, whenever we put impurities in the plasma, what we are doing is that we are converting the heat flux into electromagnetic radiation, and this allows to reduce these power loads before they can reach the wall. So now my team and I, for the first time in D3D, we have injected impurities in this newly installed slot diverter at D3D that I'm showing on the right. This is a kind of optimized shaped diverter in order to study the retention of neutrals and the impurities in the diverter. I have to say that this study has been enabled by an unprecedented diagnostic coverage in a closed diverter where these diagnostics are installed, designed, maintained by all different institutions around the US. Now, these insights on these novel and very interesting experiments were made possible by employing state-of-the-art computational modeling, such as, for instance, the SOLPS ITER code, which is the major fluid code which is used to predict conditions for ITER. I use the SOLPS ITER code routinely for my research, and for instance, for these specific experiments, I was able to introduce impurities and particular flow treatment into the code, and we were able to explain this new experimental behavior that we were seeing. This research has been highlighted by DOE and has been published and featured in journal papers. I work on both experiments and computational modeling. Here I'm showing an example of how it is to sit in the session leader in the DIII-D control room. If you have an experiment going on, it's usually a lot of fun as well. And, but at the same time, I also work on computational modeling, because I believe that for optimal scientific progress, these two needs to go together. Experiment and modeling are complementary. The experiments are needed to validate models. The models guide the experiments, and once they are validated, we can use them to predict to future reactors. So now moving towards FPP, what we are going to need to do is that we need to integrate the core, the edge, and the material as well. And also we will need a all device integrated modeling. So we have a lot of work ahead of us to prepare for this. If you can go to the next slide, please. In addition to my scientific research, I'm committed to share science with the wider public. I think this is very important that we gain support from the wider public. So I organize outreach events as well as stimulate young women in science, but also advocate for fusion, for instance, at the US Congress. This is a picture from Fusion Day on Capitol Hill in 2020. So I think that bring all these people on board is very important, and it's important that we make our case on why fusion really needs to be funded right now. Before coming to the United States, I worked at the Max Planck Institute for Plasma Physics in Germany, where I obtained my PhD, and where another important leading device is located, which is called the ASEX upgrade. I'm very excited to join the Eastern Tennessee fusion community to foster further collaboration with Oak Ridge National Lab to expand the ETEC program, while at the same time keep on working on my ongoing activities. I definitely see for the future increased collaborative program inside and outside the US in support of a power plant, but also in support of ITER. I'm an expert member of the International Tokamak Physics activity in support of ITER, and they recently joined the US Transport Task Force. So for the ETEC, so for the academia, I see ETEC becoming an increasing major center for fusion studies and training program, as well as I envision the possibility of building a new small-scale device, which on one side will enable to address key issues towards a power plant with novel and revolutionary approaches that might be difficult in a bigger size device, and at the same time to train the new generation of engineers and also physicists, which will then operate the power plant. So I think it's really an exciting time to be in future research in East Tennessee. If you want to learn more about the ETEC program or the DIII-D program, I put here the website. You can just Google it. And if you want to learn more about the diverter and core edge research or possibilities to get involved, and also in the possibility of building a new small-scale device in East Tennessee, just reach out to me. I left here my emails and my contacts, and I will be happy to talk with you further. Thank you. That's all what I have.
Excellent. Thank you very much. That was a great presentation, great overview. We're going to enter into a brief session of questions and answers, and we're going to get these from the chat. And we have 2 or 3 questions. The first one is from, I believe, Congressman Byer, and I'm going to read it and then I'm going to reformulate it just slightly. It said, on the third priority, and I think, Mickey, this is something addressed to you. On the third priority, what is imaginable regarding harnessing fusion power? How do engineers take that intense heat and transform as much as possible into electricity? So I'll add a caveat to that. Not only, it's not just how we do it, it's what do you see as the process by which we get that engineering done? What are the steps we need to take and how are we going to do it?
Right. So, I mean, regarding that chart, I mean, technical readiness level, it's a little vague as to where you are in each of these steps, but generally, technical readiness is where you have established you've established a data and a data model that is sufficient to guarantee that the next step along the way in development of the apparatus, equipment, whatever you're trying to develop can achieve. And so in this harnessing fusion power, to date, we have not done we have not collected any data along that lines. All the data so far has been on that top line where we've been producing fusion energy through various processes of ways of confining the plasma, making it hot, and it generating power. But the necessary step to create electricity is capturing that power, turning it into electricity. We have not done any of that yet, but there are a lot of ideas out there about how to do that. And in terms of various ways that you would capture the heat, as you said, it's extreme heat. It's a different type of heating process or distribution of heat than we find in any other heating system. And so it has to have specific types of solutions. So what we have to do is we have to build up a set of facilities that can allow testing of technologies to do that. And that's, I mean, companies can develop technologies, but they have to have the means by which to test that technology. And so in the program, and this was called out in this FISAC plan, was a blanket component test facility where you would have the capabilities of taking whatever technology. It could come from the government program, it could come from the private program, and put it into this test facility and test whether or not it delivers on the functionality and the performance that you need to put it into a pilot plan of the future.
Okay, very good. Thank you. We have, I think, time for just one more question, so I'm going to go to this one. I think this may be addressed best by Kathy. For many ITER partners, their follow-on to ITER is a government-led program, for example, the demo in Europe. So these programs are connected into existing ITER member domestic organizations. How do private fusion companies in the U.S. gain access to the 100% of the knowledge that was identified as a key benefit of U.S. involvement?
So pretty simple, pretty quick answer to that, perhaps not entirely simple. What we're doing is we're putting together a process that will be clear and easy to follow. So a request comes in, it goes through the process, and the idea is to turn the information around as quickly as possible. At this point, we don't have that process developed, so we're handling these things on an as-asked basis. So if somebody has interest or would like access to ITER information, at this point, just send your request to the project. You can send it to me. You can find me on the ITER website, and we'll do it that way. But again, the idea is to make this a seamless process. One of the complications in this, just to point out, is with some of the work that's going on, there's prior IP that a company brings in for the work that they're doing. So we, of course, can't release that, but what's developed under ITER is fair game.
Okay, well, thank you very much for that. With that, I'm going to go ahead and close the panel. I'd like to thank our speakers for excellent presentation and discussion. So thank you very much. Eric, I'll turn it back over to you.
Okay, thank you very much, Lou, and thanks to all of the panelists and their presentations. I find it extremely encouraging, all the work that's being done in the R&D front, and very pleased to hear that UTK is going to be a emerging leader in fusion studies. That's very exciting for us here in East Tennessee. We are now moving toward our second break.